Welcome back to the deep dive. Today we're doing something a little different. Instead of articles, we're using a set of specialized sources.
It's basically a professional certification blueprint.
Exactly. It's the knowledge you need for the NCA-AIIO exam, and we're using it as our map.
And the beauty of that is it just cuts right to the chase. It shows you the high value points across the entire AI stack.
From the pure theory all the way to the server rack.
Yeah. And if you can answer these kinds of questions, it means you don't just know the definitions, you actually understand the relationships between the hardware, the software, and the data center itself.
It's a holistic view.
Mm-hmm.
And it's aimed at professionals who, need to move fast.
Right.
So our mission today for you is to distill all this down into 3 logical layers. First, we'll hit the foundational theory.
Then the specialized hardware. The really cool stuff.
And finally, we'll get into the operational infrastructure, how you actually make all this work in the real world.
We're basically taking the journey from an abstract idea all the way down to the physical limits of power and cooling.
Let's do it. Let's start right where the models themselves start.
Oh.
How they learn.
Okay.
So when we talk about how modern AI models learn, especially for things like, say, image recognition or fraud detection, there's one main paradigm that really stands out. It's the one where the model is trained on a huge labeled data set, meaning for every piece of data you feed it, you already know the correct answer.
And that is the absolute cornerstone. That's supervised learning.
Supervised learning. Why does that one still dominate so much?
Well, it all boils down to predictability.
Yeah.
The training process is supervised because you are constantly telling the model, nope, that was wrong, this is the right answer.
You're correcting it against a known ground truth.
Exactly. So the labeled data is like the curriculum for the student.
Right.
And this lets the model learn a really clear, really reliable map between an input and a known output. It's why it's the go-to for, say, classification, like sorting spam from not spam.
Or for regression, like predicting house prices.
Precisely. But the key thing to remember, the operational insight, is that it's all dependent on the quality of those labels.
Garbage in, garbage out.
100%. If your labels are biased or just plain wrong, your million-dollar model is flawed from the very beginning.
That is a crucial takeaway.
Yeah.
Okay, so that's the method. What about the architecture? When we move into deep learning, what is the fundamental building block?
The foundational unit, really the heart of deep learning, is the artificial neural network, the ANN.
And the origin story of the ANN is fascinating. It wasn't just invented in like a math lab somewhere.
Not at all. It's explicitly inspired by the biological neural structure of the human brain.
Wow.
Yeah. I mean, ANNs use these interconnected layers of artificial neurons. Each one processes data using weighted connections, activation functions. It's all meant to mimic how our own neurons fire.
So the weights and the connections are what the model actually learns during training.
That's it. It adjusts those to find the complex patterns.
So we start with this really elegant, biologically inspired idea, but turning that into industrial power. Something that can process petabytes of data.
Yeah.
That takes some serious horsepower.
Oh, absolutely. A standard CPU just falls over.
Which means we need to talk about specialized hardware.
Exactly. We have to accelerate the math. Deep learning is just massive, repeated matrix and tensor multiplications over and over again.
And a CPU is a generalist. We need a specialist.
We do.
So what are the dedicated components inside modern GPUs, let's say Nvidia GPUs, that are built solely for those huge matrix operations?
The answer there is tensor cores.
Tensor cores.
They're purpose-built accelerators. They are embedded right into the GPU architecture.
Okay, so why are they such a game changer compared to just, the regular GPU cores?
It's all about efficiency. And precision management, they crunch those dense matrix operations so much faster because they're optimized for something called mixed precision arithmetic.
Mixed precision. What does that mean in simple terms?
Well, think of it this way. When you're training an AI model, not every single calculation needs, the highest possible level of mathematical precision.
So you don't always need 32 decimal places.
Exactly. Full precision is like using a heavy industrial calculator for everything. Mixed precision is like switching to quick mental math for the parts where it's good enough.
You get the answer faster using less power.
And less memory, without losing the essential accuracy the model needs to learn. Tensor cores are specifically designed to handle these lower precision calculations, and that gives you a massive boost in training speed.
They're the definition of specialized hardware.
They really are.
But, okay, acceleration is great, but once you scale up and start linking multiple GPUs together, which you have to for the big models, don't you create a new bottleneck?
You do. Instantly. A communication bottleneck.
So how do those super fast chips talk to each other inside a server without slowing down to wait for some older interface?
The solution that bypasses that problem is NVLink.
NVLink.
It's Nvidia's high-speed point-to-point interconnect.
And the key thing is that it allows for direct GPU to GPU communication. Where?
Critically, within a single server. This is so important because traditional interconnects, like, say, PCIe, they're general purpose. They're slow, they have high latency.
They weren't built for this job.
Not at all. NVLink provides way higher bandwidth and lower latency. It's like a dedicated superhighway just for the GPUs.
And without it?
Without it, your very expensive tensor cores would spend most of their time just sitting there waiting for data. Your performance would be terrible.
So NVLink solves the internal communication problem. Now, what about a different problem? A huge operational headache for anyone running a shared AI data center.
I know where you're going with this.
How can one incredibly powerful, expensive GPU be shared? How do you partition it so multiple different users can use it at the same time, securely and efficiently?
That is the domain of multi-instance GPU, or MIG.
MIG.
MIG lets you partition a single physical GPU into multiple isolated instances, up to 7 of them, actually.
And isolated is the key word there. It sounds like more than just standard virtualization.
Oh, it's way more. Each MIG instance gets its own dedicated compute cores, its own dedicated memory, and its own dedicated bandwidth. The isolation is physical.
What does that guarantee for the person paying to use a slice of that GPU?
It guarantees 2 things. First, security. One user can't snoop on another user's memory. And second, and this is huge, predictable performance.
Meaning one person's crazy workload won't slow everyone else down.
Exactly. No noisy neighbor problem. MIG is really a financial tool. It stops a $20,000 piece of hardware from being tied up by one tiny job.
Okay, so we've got the theory, we've got the chips, and we have the connectivity. The model is trained, but now it has to be deployed.
Right. We're shifting from the long, expensive training phase to the high-volume, low-latency inference phase.
Where every millisecond counts.
Every single one. Training can take weeks, but inference happens millions of times an hour in production. You have to take that big, clunky trained model and squeeze every last drop of performance out of it.
And the key software tool for that job is what?
That would be a library from Nvidia called TensorArt.
TensorArt. So its job is specifically to optimize an already trained model for inference.
Yes, for high-performance inference.
What kind of heavy-duty techniques does it use to, cut down latency and boost throughput?
Think of the trained model as a newly built race car. TensorArt is the pit crew that tunes it for the track. It performs some really aggressive optimizations.
Like what?
Well, the big ones are layer fusion, where it combines multiple computation layers into a single, more efficient operation. Then there's precision calibration.
Shifting to that lower precision math again for more speed.
Exactly, moving from, say, FP32 down to INT8. And it does really sophisticated kernel optimization to make sure the code runs perfectly on that specific GPU. The whole thing just shrinks the model's footprint and slashes the latency.
So we've got a perfectly tuned model. But in the real world, a production environment has tons of different models.
Yeah.
Some built in TensorFlow, some in PyTorch.
An operational nightmare.
Right. Running separate infrastructure for each framework would be crazy. What's the solution that unifies all of that?
That is the huge benefit of the Triton Inference Server. It's like a central hub.
And what's the key flexibility it offers to the poor DevOps teams managing all this?
Its main strength is that it supports models from multiple AI frameworks at the same time.
Simultaneously?
Yes, simultaneously. A single Triton instance can be serving models from TensorFlow, PyTorch, ONNX, you name it, all concurrently.
So you don't need separate infrastructure stacks?
You don't. It drastically simplifies everything. Version control, monitoring, scaling.
Yeah.
It just makes production management 10 times cleaner.
Okay. Triton handles the serving. Let's step back one more level to the development process itself. Speeding up AI isn't just about faster chips. It's about cutting down that initial development time.
The cost and time to train from scratch is astronomical.
So what resource does the NVIDIA NGC catalog provide, besides just software containers, that really shortens that path to deployment?
It's the pre-trained AI models. This is a huge, huge asset.
How does using a pre-trained model directly save a developer time and money?
Look, training a big foundational model from zero can cost millions of dollars and take months of GPU time. It's just not feasible for most companies.
Right.
By grabbing an optimized, validated, pre-trained model from NGC, Developers are starting like 90% of the way to the finish line.
They just have to fine-tune it for their specific task.
Exactly. That's called transfer learning. It just dramatically reduces development time and compute cost. It makes AI accessible so much faster.
So we've gone through the whole logical stack. Now we have to face the physical reality of running this stuff at scale in a real data center.
The messy part.
You've got this cluster packed with expensive GPUs. They need to be fed a constant stream of data. If that data delivery is slow, your tensor cores are just sitting idle.
Which is just capital being burned.
So what is the single most important characteristic that data center planners need from their storage system for an AI training cluster?
High read throughput and low latency. Period. End of story.
And that's non-negotiable. Standard enterprise storage can't cut it.
No way. It can't keep up. AI training is all about loading these massive data sets in small batches over and over really fast. If your storage is a bottleneck, the GPUs get starved.
Starved for data.
Think of the GPU as a Formula One engine. High-throughput storage is the industrial-grade fuel pump that keeps that engine redlining. Without it, you're just idling in the pit lane.
That's a great analogy. It really drives home the financial impact of slow storage. Okay, final physical constraint. Power and heat.
The big one.
We're asking these chips to run at peak capacity for weeks on end. That generates a staggering amount of power consumption and heat. So what's the absolute non-negotiable infrastructure requirement for deploying a dense AI system like a DGX cluster?
Planners absolutely must account for specialized high-capacity power and advanced cooling solutions, and that's not a recommendation, it's mandatory.
Give us a sense of the density we're talking about here. When you say advanced cooling, what does that actually mean?
Well, in many cases, we're talking about direct liquid cooling. These systems can consume several times the power of a standard server rack, and all that heat is in a tiny physical space.
So you can't just plug it into a normal rack and hope for the best?
You can't. Relying on conventional air conditioning will guarantee system instability, or worse, outright hardware failure. You need specialized infrastructure, dedicated power distribution, complex liquid-to-air heat exchangers, all of it.
It's essential for stability, for performance.
And for protecting the longevity of that incredibly expensive silicon you just bought.
So to make the elegant, brain-inspired ANN a reality, we first have to build the data center equivalent of a small power plant and a giant refrigeration unit just to stop it from melting.
That's a pretty good summary, actually. It ties the whole loop together.
It really does.
Thank you for diving deep with us.
We'll see you next time.